We'd like to analyze a physics problem called the rocket problem, in which we have a continuous mass transfer. Let's see what we mean by that. Let's consider a rocket launching. So here's a classic example of a rocket that's launching off in a gravitational field. As the rocket starts at rest, it starts to burn fuel and ejects the fuel backwards. And as the ejected fuel backwards is producing a thrust on the rocket, and you can see as the rocket starts to rise, it's starting to accelerate upwards as fuel is ejected backwards. Now this process goes on for some time interval, and a lot of fuel is ejected backwards during that time interval. In this particular case, we could analyze the situation from the ground frame of the rocket, from the ground frame of the Earth, and the fuel is ejected backwards relative to the rocket. Rocket moves up forward. So how do we analyze this situation? If we just looked at the rocket when the rocket initially launched, the mass of the rocket is the dry mass of the rocket plus all the fuel in there. It's at rest. In a state much later on, the mass of the rocket has decreased and the speed has increased, but we can't just compare this initial to this final state, because throughout this process there was a continuous mass transfer. Fuel was ejected backwards. So how do we analyze these types of continuous mass transfer problems? And the key is, again, identifying states. So for a continuous mass transfer problem, we always have to choose a reference frame. So here in our example, we were choosing the ground frame of the Earth. And then we want to identify two states. We don't want to identify the initial and the final states. We want to pick two arbitrary states that are separated by a small time interval. So we can take a state at time t, and then our second state occurs at a small time afterwards, time t plus delta t. And what we want to do is now represent the state changes by momentum diagrams. And that will lead us to a differential equation, which is called the rocket equation, and that's how we'll analyze all continuous mass transfer problems. In applying the momentum principle, our first thing is just to choose a reference frame. So in our example, we're going to choose the ground frame of the Earth as a reference frame. Now, the next step is the key to these processes. Instead of choosing some initial state where the rocket is at rest and some final state much later on, we want to choose two states that are separated by a small time interval, delta t. So our first state at time t, and our second state we choose at time t plus delta t. Now, the next step is that we have to identify what is our system. And so in this case, our system is going to be the mass of the rocket at time t. That mass is the dry mass of the rocket plus all the fuel that's still in the rocket at time t. And this mass will stay the same between times t and t plus delta t, even though some of the mass has been ejected downward. So our next step is to look at that mass conservation of the system. We would now like to apply the momentum principle to analyze the motion of the rocket. So what is our momentum principle? We know that the external force at time t is equal to the rate of change of the momentum of the system over t. Now, recall, we're going to actually use the formal definition of a derivative to write this as a limit as delta t goes to 0 of the momentum of the system at time t plus delta t minus the momentum of the system at time t divided by delta t. So in order to analyze the rocket, what we need to do is separately analyze the momentum at our two states. So we have a state at time t, and we have a state at time t plus delta t. And our goal will be to analyze the system momentum at time t, and separately the system momentum at time t plus delta t. And then we can apply the momentum principle. So let's begin by analyzing the system at time t. So recall that at that time, we had our rocket, and this is our time t. And the rocket had a velocity, v of r of t. And what we identified, the mass, mr of t, recall this was the mass, the dry mass of the rocket, and the mass of the fuel. And so now it's very simple to write down the momentum of our system at time t. That's equal to just the mass, mr of t, times the velocity of the rocket at time t. And so we can use that in our expression for the momentum of the system. Now our next step is to consider the system at time t, t plus delta t. Now recall, we still have the rocket, but the mass of the rocket has changed. That's inside the rocket. So this is dry mass of the rocket plus mass of the fuel. But recall, some of the fuel has been ejected outwards. So how do we depict that in our momentum diagram? Well, let's just symbolize that by a certain amount, and we're going to call this delta M fuel. Now, what we need to do, again, is to have our velocities. So here, the velocity of the rocket is now the velocity at time t plus delta t. And what about the velocity of this fuel that's being ejected? Well, in our problem, the fuel is ejected at a speed, at a velocity u relative to the rocket. So what we have is u is the velocity of the fuel relative to the rocket. But we've been choosing the ground frame as our reference frame, and the rocket is moving at a velocity at time t plus delta t with respect to that ground frame. And so recall that the velocity of the fuel in the ground frame is equal to the velocity relative to the rocket plus the speed of the rocket with respect to the ground frame. And that's what we're going to draw on our diagram as V fuel. And so now we can finish this analysis, and we'll apply that next, is to write the momentum of the system at time t plus delta t. Now this is going to have two terms. It has the mass of the rocket at time t plus delta t times the velocity of the rocket. And we also have to add mass of the fuel times the velocity of the fuel with respect to the ground. And now we have the momentum at time t plus delta t. So we have both of our pieces here, and we still have a little bit of analysis because we'll use our mass conservation equation to end our relative velocity condition to simplify this expression. So we'll do that next. So now we wrote down the momentum of the system of our rocket at time t and the momentum of the system of the rocket at time t plus delta t. Let's make some simplifications in our notation just to make our calculations a little more easy to read. So the first thing we want to do is we want to say that the mass of the rocket at time t, this is the mass of the rocket plus the mass of the fuel in the rocket at time t, we're just going to denote that by mr. And keep in mind that when you write the mass at time t plus delta t, we'll write that as the mass at time t plus delta mr. This is precisely how you define a differential. Even if this quantity is negative, you always write the difference, m of r of t plus delta t, minus m of r t equal to delta mr. That's how we write a differential delta mass of the rocket. So the mass of the rocket at time t looks simpler, m of r plus delta mr. So those are two ways of simplifying our expressions for the terms that are appearing here and there. Now, the next thing was recall from our mass conservation that we had the condition that delta M fuel was equal to minus delta M rocket. So now we'll take those two simplifications, and now we'll write down our system momentum at time t. That's very simple. mr v of r at time t. And we'll now write the momentum at time t plus delta t. Well, we have the first piece, which is mr plus delta mr times the velocity of the rocket at time t plus delta t. Now, be careful here because we're going to use our conservation of mass condition to replace delta M fuel with minus delta M rocket, and we'll use our expression for the velocity of the fuel in the ground frame of the rocket. So we have minus delta M rocket times the velocity u plus v of r of t plus delta t. And this simplification, we'll write equations 1 and equation 2, will enable us to apply the momentum principle in a very transparent way. And that's what we'll do next. For our rocket in an external force, we had the rocket equation, which we wrote as mass of the rocket. Now remember, this is a function of time times the derivative of the rocket, dr dt. And we also had this second term that came from the ejecting fuel. Now, from our mass conservation equation, we can rewrite this equation as a differential relationship that the change of mass of the fuel in time is equal to minus the change of the rocket. It doesn't matter which side we put the minus sign on. So now I want to interpret this equation in a different way, and it will come back to what we mean by our system. Let's first off bring this other term over to this side. So we have plus dmr dt u, and that's equal to mr dvr dt. Now, separately, let's make this substitution again and go back to our fuel term. So that's minus dmf dt u equals mr dvr dt. Now, notice that over here we have mass times the acceleration of the rocket. So if we just rethought our system as simply the rocket, mr, then we have two forces acting on the rocket. The external force might be the gravitational field, but we have a new term here, which we're going to refer to as thrust. And so our thrust can be thought of as an external force simply on the rocket as a system. And that's equal to minus df dt u. Now, again, if I chose j hat up, let's just look at this in components, then our thrust as a vector, we'll write it as a y component, is equal to minus dm fuel dt. Now, what is that relative speed? Well, the fuel is being ejected backwards, so that's minus mu j hat. The external force, by the way, would be minus mg j hat if it's near the surface of the Earth. So we have another minus u j hat, and we see that we have a positive thrust force in the vertical direction that is giving us an additional force other than the gravitational field. And in Cartesian, in our unit vectors here, we have minus mg plus dm fuel dt times u is equal to mr dvy dt of the rocket. And so this is the rocket equation in components.